welcome to ME 370, System Dynamics and Control. We weren't sure what class it was until I scrolled up to the top of the page. Now we're clear. Oh wait, that thing's not on. Well, that'll fire up. So this course is a wonderful course. It includes both system dynamics and control. Last semester we did ME 345, which included system dynamics and electronics. Okay? And so we got a little bit of that flavor, and we're going to get some more of it. This course is effectively a continuation of that previous course. So ME 345 leads right into this course. So being successful at ME 345 is important for this course. We will be using more lumped parameter modeling, more linear graph modeling in this class. But we're going to go beyond where we were last semester. So approximately, so I'll talk a little bit about system dynamics and control to start things off, and then we'll go through the specifics of the syllabus. Okay? So first of all, we talked about system dynamics in pretty great detail last semester, but I'll refresh your memories. We talked about how the system dynamics approach is thinking about the system, thinking about some part of the world from a specific perspective. You're trying to understand its behavior from a very specific perspective. So you're going to treat it like it follows some mathematical model that you have, okay? And one of the ways that we do that is we write a differential equation down to describe the system's dynamics, okay? Differential equations that we've used have been Newton's second law. We've used the so-called elemental equations of the capacitors, of inductors, of resistors, of springs, and all kinds of other elements. Rotational mechanical systems as well, moments of inertia. So torque equations versus force equations. And these equations describe the dynamics of the system to us, along with the constraint equations, the equations that we use to describe how those elements are connected. So those would be the continuity and compatibility equations, which were like the KCL, Kirchhoff's current law, and KVL, Kirchhoff's voltage law, from electronics proper. So we have these mathematical models that describe the dynamics of a system. And it turns out that a lot of those mathematical models, those equations, are very similar, even between and among the different energy domains. So in mechanical systems, we have equations that look like the same as in the electrical systems. And we have electromechanical equations that relate them. So we can kind of treat them as one system with multiple energy domains within it. We're going to extend that in this course. In mechatronics, we stuck with electronic systems, translational mechanical systems, rotational mechanical systems, and then the transducing elements that move energy from one domain to another, right? In this course, we're going to further extend that to include thermal systems, so heat will be flowing around, okay, and being stored places, and also fluid systems. So we'll add fluid, so like water that's flowing around in pipes, for instance. So again, remember that we're specifically focused on lumped parameter modeling in this class. So we're going to treat a pipe as like one or two lumped parameter elements, like a fluid resistance and a fluid inductance is one way to describe it. Inertance is what we'll call it. And just as we've done with mechanical systems, we treated a body like it's just a point mass with a spring attached to it or something. We've done that sort of simplification, that lumped parameter modeling. We'll do that again in this term. And it's good to keep in mind how that's related to what you're learning about in your thermo class or your fluids class. And especially, I would say, fluids or heat transfer in next year. You're thinking about where heat is distributed throughout a body, and you're keeping track of every location in the body, what the heat is for that location. We're assuming that we can just sort of treat it as one body that has some temperature. For instance, for heat, the whole body would be considered to have one temperature. So it's different. It gets you different things. So maybe you care about the temperature difference between one part in the body and another part in the body. Well, the type of analysis that we're doing is not very conducive to that sort of analysis. If you're interested in that, you would need to go to a more detailed heat transfer perspective, and really probably a finite element perspective. And what we're doing here can be transformed into that kind of thing, where you take smaller and smaller lumped parameter elements, where you, instead of having one for a body, you could have 10,000 for a body, and then just take like little voxels, they're called, so volumetric pixels, that are describing each little bit of the body. You can do that, and so that would be a finite elements sort of approach to modeling, and that's beyond what we're going to focus on in this class. I think I'll give you guys one heat transfer problem though that does that, and it shows you how you can use this, extend this stuff to finite element approaches. So so we're doing this sort of system dynamics approach, lumped parameter modeling. The mathematical models that we'll get will be ordinary differential equations, because they're not distributed through space, just time. So we have ODEs to solve to find out what the system will do in response to some input, right? So our systems are like a box, and we have inputs going in, and we have outputs coming out. And remember, we've used state variables inside, so we could put X down here, state variables inside the system describing what's happening in there. So we've got this conception of a system as having inputs, states, and outputs. And the first half of the semester, well, actually, the first 2/3 almost of the semester, we're going to do more and more analysis of our system models, okay? So the models can be, modeling what's in there. You can have like a state space model, which is the sort of mother of all models. And a linear version, which most of our state space models will be linear in this class, is dx dt. So what is x again?
State variables.
Yeah, it's the vector of state variables, or the state vector. If it's linear, we can write it ax, some matrix A, times the state variable vector x, plus bu. And the output can be described algebraically as cx plus du. So this was what we spent a lot of time learning to derive from linear graph models, right? We learned how to describe the elements in terms of elemental equations, and then the network of all of the elements being connected, and in terms of continuity equations and compatibility equations. And then we were able to construct these state space models. So those are like the nicest models to have. So usually, if you want to model a system, like this is the way to go in many cases to construct a state space model. We also learned a little bit, for just in passing, about transfer functions, right? And they were like something like h of s equals some polynomial in s in the numerator divided by some polynomial in s in the denominator. I don't know why I chose to put 1 as the coefficient there, but I did. And this is the ratio of the output over input in the Laplace transform domain, right? So S is the Laplace transform S. And we talked about those just in passing. We're going to talk about them in more detail this semester. But we used these, we found these transfer functions as a bridge to go from the state space model to the input-output ODE. Model, I guess. Which, for a second-order system, looks like, well, I'll just write it like this: y double dot plus 2 zeta omega n y dot, where dot is a time derivative, plus omega n squared, y equals some forcing function. So a single scalar input-output differential equation. The state space model has an order n, which is the number of state variables. If you transform that into an IOODE, then you have an nth order scalar differential equation instead of a set. So the state space model is a vector differential equation. Or you could think of it as being a set of n first-order scalar differential equations. It's equivalent. So you can go back and forth pretty much by inspection here. Remember, the way that we did this transformation was that h of s equals c times si minus a inverse b plus d. So this is matrix operations, right? These are matrix operations. So this is the identity matrix of the size of A. So you need to do matrix subtraction, scalar multiplication of a matrix, and then an inverse of a matrix, then matrix multiplication, and then matrix addition. So you got to be able to do those linear algebra operations pretty much from the get-go here. Linear algebra is a prerequisite for this class, but if you need to brush up on it, or there are a couple people who did not take linear algebra before this and have like snuck into the class, let's say, you're gonna want to make sure that you know how to do those, even if you don't have like a deep understanding of it. Maybe you're gonna work on the linear algebra like during the semester. At least be able to do the operations you need to know how to do. Maybe you're just memorizing it for now and you'll understand it better later, but it's important to do that. So that's one place linear algebra will come in. Another place that some maths will come in is in this IOODE model. If we have it in this form, we want to be able to solve it in terms of our whatever method we choose, but typically the method of undetermined coefficients is how we would solve this. And this is what we did last semester, right? So you could solve with the method of undetermined coefficients. And if you're needing a refresher on that, there's that little primer series of like 4 videos that I have up, and then the notes. So we've done that. we aren't going to be solving anything in the Laplace domain, so you could take the inverse Laplace transform. I mean, I'm not going to like promise that we won't, but it's not a focus of the course. Because taking the inverse Laplace transform is a great way to solve things, and so you could, instead of doing the method of undetermined coefficients here, you could take the inverse Laplace transform in the Laplace domain and get your solution. So some of you are more comfortable with that than you are with the method of undetermined coefficients. It's fine with me, but I'm also, when I write my solutions, I'm going to do it all this way. So if your solution's in Laplace and you don't get the right answer, I'm going to have a harder time knowing where you went wrong because I don't want to have to solve it out multiple ways because it's just a lot of work. But if you get it right, then I don't care. It's just fine. You're good. I'm not saying you won't get partial credit, but it's harder for me to tell where you went wrong. Okay. What we're going to start out with is we're going to talk about some different solution techniques and easier ways to solve these IO ODEs. So that's what the My Notes Chapter 5 are going to be about, and the textbook, Rowland Wormley's textbook, Chapter 8 is going to be about. Pretty useful, some different properties of linear systems and useful techniques for solution. Then we're going to learn how to solve the state space model equations directly. Okay, so we can solve them. And when we do that, we're going to have to linearize this. Or I guess I shouldn't say we have to. It's much easier to solve the system if you linearize it, meaning that A matrix is a diagonal matrix. And you can do that by transforming the state variables into a state variable vector, state vector, into a new basis, a very special basis that diagonalizes the A matrix. There are, for most of the, well, for all the systems we're going to consider in this class, there will be a diagonal form. There are some cases where you can't diagonalize it completely, and those are a little tougher to deal with. It's not bad, it's just like a whole other thing. So we're not going to go into details of that, but I think there's an appendix I put in the notes that talks about that. It's Jordan canonical form instead of diagonalized form. So you're going to be able to diagonalize this with a basis transformation. Now, that is something you learn in linear algebra, right? How to transform bases in a vector space. Again, best if you've had linear algebra. If you haven't, by the time we get there, just like try to learn enough of that, like flip ahead in your text, try to learn enough of that to just keep up with what we're doing, and you'll get a deeper understanding when you get there in linear algebra. Another thing we're going to do, so in order to transform into that basis, we're going to have to find the eigenvalues and eigenvectors of the A matrix. So finding eigenvalues and eigenvectors is another thing that you learn in linear algebra. Some of you might have learned it also in differential equations, depending on who you took. And so you also are going to need that material when we get there. So that's coming up like next week, the diagonalizing and the eigenvalues and eigenvectors. And so that part could be tough if you haven't already taken linear algebra. Fortunately, it's a prerequisite, and most of you have taken it already, so that's good. Great. So now let's talk about control for a minute. So there's more to, there's like a whole lot more to system dynamics than what we've discussed. Oh yeah, I'll mention, and then we're also going to add fluid systems, like I said. Then we're going to learn about how to do some numerical solution techniques, so like how to use MATLAB to simulate. Thank you. It continues.
Can we get a sneeze, please?
Nice. I like it. So we're going to take the fluid systems, the thermal systems, and we'll learn about those. And then we're going to also do sinusoidal inputs and outputs, which we're going to then take and extrapolate into the so-called frequency domain. So we're going to do a lot of stuff in the frequency domain in system dynamics as we proceed. So if you've ever heard terms like Bode plots. That's what's coming. Or like resonance or vibrations analysis. Like these things all come out of system dynamics theory. And so you're going to get like a good foundation for that. So when you take vibrations as a senior, you'll be able to already have a good feel for what you're going to do. So it'll be fun. Everybody's seen those like cool demonstrations of like resonances that have gone out of control, like these modes that like make bridges go crazy and all that. So that's one of the things you can do with this. Okay, and then we're going to switch gears to control. Okay, and control is the idea we want to make this output of the system something that we want. Okay, so I don't know, let's pretend that it's a single link in a robot arm and you want to go from maybe this angle to this angle, and your output is the angle, and you want your output to be at, say, 60 degrees, okay? But currently it's at 0. Well, let's call this 0. And you want to be at 60. So if you understand the system's dynamics really well, you have a good model for it, you can figure out what input you need, like how much torque you'll need, for instance, to take it from 0 angle to 60 degrees. Okay? Great. If you know the system perfectly and you did a great job of modeling, you got it. You nailed it. Trouble is, you're there, say, but you missed by like a few degrees. But then you want to go another like 30 degrees over, say, and, well, I guess it would be at 90 then. You want to go another 30 degrees up. You started off from a few degrees off, and this one's going to be a few degrees off too, so then you've accumulated a little more error. And then you want to go another 10 degrees, and you accumulated some more error. You started off a little bit off, and then like you just accumulate the error. More and more error gets accumulated as you keep doing this. So you lose track of where you are in the system because your modeling wasn't perfect. In addition to having an imperfect model, there are disturbances that come in. So for instance, in the robot arm situation, maybe there was a gust of wind that came up, or somebody bumped it, or the block that it picked up was heavier than you had anticipated, and that input has some offset disturbance associated with it. And you are if you don't know these things, which you can't know about everything beforehand, then they're just going to affect the output, and you're going to have no control over that. It's just going to happen, right? So this idea of like changing what the input is in order to change the output, it's a good idea, but it's hard to do well in what's called open loop, which is what we have here, which sort of implies what the solution is that we're going to use. And the solution is feedback, okay? I'm going to redraw our system down here. So here's our system. And so say it has transfer function g of s. And we have an input coming in, u, and we have an output coming out, y. Now, what we're going to do is we're going to measure what the output actually is. We're going to feed it back, okay? When we feed it back, we're going to compare it to what we want that output to be, okay? And the way that we compare it to what we want the output to be is we subtract the actual value from the commanded value, or the value we want. So this is a summing junction with this being plus and this being minus. So y being the actual output, we subtract it from the commanded output. So the command is what we want y to be. In the first case, we wanted y to be 60 degrees, but the actual y was 0 degrees. So we got our measurement of it, and we compared it, and we got an error of 60 degrees that came out. Okay? So the error signal is there. So if there's any difference there, if the difference is 0, then you don't need to do anything, right? You're good. Your command and your output are the same. But if they're different, then you're going to get some non-zero error here. What we do is we feed that error into another block, another system. And this other system is the controller. The controller has a transfer function of its own. Let's call it C of S. And it takes this error signal and it decides what should we put into the system to correct for this error. Okay? And choosing what goes in this block is what a lot of control theory is about. What is the best thing to put in that block? Given an error, what input should you put into the system? Sometimes this is called, when it is in this closed loop here, it is the input to the system, but sometimes we call it the control effort. So for instance, your actuators in the system might be like 3 motors, and those are going to be how you exert control effort on the system. So say you have a robot with like 3 links and you have 3 motors. Those are your 3 inputs to the system, and that's what your control effort is. Like how many volts are you going to put in across each motor, for instance. Okay, so there are, so my PhD was in controller design. So like it's like you can do a whole PhD in just how to pick what this block is effectively. So there's a lot to it. However, like 90%, I don't know, I've heard different numbers, but like a lot of the controllers that are out there in the world are of a certain variety called PID controllers. And that stands for proportional, integral, derivative. And what these 3 words are describing are 3 terms in a transfer function, in the controller transfer function. So C of S, there's going to be a proportional term, Kp. And what it's going to do is just going to take the error, whatever it is, and scale it by some gain, Kp. Now, when you do that, you have some behavior that looks a lot like a spring. So you know how a spring has its restoring force to equilibrium proportional to how far away from equilibrium the spring is compressed or stretched, right? So how far you are away from your command is essentially how far that proportional gain or that proportional restoring force is going to push back to the equilibrium value or the command value. So that's a good one. That was like, you can do a lot of control with just a gain there, proportional gain. And we'll talk about the limitations of that when we get to the details, but that's one way to start. The next term is the integral term, so Ki. And it is multiplied by a 1 over s, which is the Laplace s, so it's a so-called integrator, right? A 1 over s is an integrator. And the 1 over s, what it effectively does is it takes that error signal. So say e, we'll just say we have a scalar e. And over time, that error is maybe doing this sort of thing. But maybe it's staying small. So the proportional restoring force isn't going to be, and I'm saying restoring force, but like this could be a voltage or restoring whatever the variable is, but we think of it like a spring sometimes. So restoring effort is going to be very small because you have a very small offset from your nominal value, the value that you want, your command. So your error is small, so the restoring force from proportional gain is small. What the integrator does is it integrates, well, it starts, of course, here, and it just integrates all of this. And what that allows it to do is it'll build up. So like if it has a little bit of an offset in steady state, it's just sort of stuck here, a little bit off, it'll grow over time until it brings it back to equilibrium. Okay, so we'll talk a lot about that. That'll be a whole discussion that we'll have about how the integrator does that. And then you have the derivative term, so kd times s. So s is a differentiator. And what that does is it differentiates this error signal. So say you had the error signal again, and this time the error is going along like this maybe, and then like it suddenly just shoots up. Okay, maybe there was some big disturbance, like Hal like tipped over a refrigerator into the robot or something. So like it just like whoosh, shot up. The error is like significant. Like something big happened. So what we want to do is we want to react to that, right? We want to restore back. But the integral one is, it's just like integrating away. So it's not going to be very affected by this immediately. The proportional one, it's going to take it a little bit until it gets high enough for the proportional one to really kick in. So we want it to react quickly. So what we do is we have a derivative term. So when this derivative, the slope of this gets high, that means the restoring force can immediately react to changes in the error that happen quickly. Now, this one's dangerous because what we're usually doing is getting a signal that's actually noisy. So if this signal is noisy, so I'll just draw another one on top of it here. If it's noisy, we're switching back and forth between huge positive slopes and huge negative slopes. If you just use the last, like, say, 2 data points or something, you're going to get huge positive and negative slopes, and you're going to get this, you can see these controllers like start to jitter, and I'll bring in a controller and we'll play with stuff later on, but you can get like jitter, or you can get unstable systems pretty easily with the derivative term. So you have to be a little careful with it, and we'll talk about how to be cautious with it and all that. Okay, so that's like what we're going to do is we're going to learn more about PID control, and we're going to learn how to do the design and simulation of it and how to design these controllers. And that'll give you guys a really good foundation in controls. And then if you want to take the next step of it, in the fall, I'll be offering Control 1, which is a new course that does a little bit deeper look into controls. So, yeah. Okay, so that's an overview of the material in the course. Now let's talk about how to actually navigate this course. Office hours, this is the location. There are 2 sections. I don't care which one you come to, the lecture. I'll post the videos. And just when you take exams, do come to the correct section, because otherwise people tend to clump up in the later section. Oh yeah, this is the course website. It's pretty easy to get to my webpage. Even if you just Google my name, you'll find it. Go under the courses tab, and it's the latest one. And this is spring 2019, believe it or not. Textbooks, same Rowell and Wormley text from last semester. I'll often be using RW as the abbreviation of that, and then NICE, so NII uses that. We'll use in the last 6 weeks, 7 weeks of the course. So it's a great textbook. It's like there are only 2 standard controls textbooks. It's one of the 2. It's pretty good. Great. And then I also have, of course, the dynamic systems notes from last semester. If you go here, you have this page, and here's the PDF of everything. I need to remember to send a copy over to the copy center so you can get them printed out. Wednesday, again, I'm going to do a spot check. Chapter 5 in those notes, I'm going to want to see you guys have printed out. If you don't have them printed out, then I might reduce your quiz grade for next week. So, we're in Chapter 5, so there are 3 lectures in Chapter 5 to print out. Bang, bang, bang. We'll do the first 2 on Wednesday and the last one on Friday. So same story there. Print them out. I'll be going over them in lecture and then doing fill-ins here, where I'll be writing y of t equals something, and you'll be able to write on yours and keep that copy, and you'll be able to bring those into exams. And that's one of the most important reasons to do that. So you can take them into exams. Anything that you write or things that I circulate for notes like these can come into exams. Textbooks and other things that are printed off are not allowed. So, great. So either go to the copy center and get them all printed out at once, or you can print them chapter by chapter if you want as we get there. Some of them might get revised as we go, and if that happens, if there's a significant revision, I'll let you know to print a fresh copy of that lecture. Video lectures, same thing. There are none up there now because I figured the second one would be better than the first one, and so far I'm nailing it. So yeah. I'll post this one instead of because I have 2 sections of this class, I usually post whichever one I think is better. Or if I have technical difficulties on one. I think I worked around this freezing face thing happening in this morning. And so I'm all right, I found, I think, a way around it so that now my face shouldn't freeze. If you want to look at last year's lectures, there's this playlist, there's a link down there. If you click on it, it takes you to that. And things are going to be a little different, but they're not going to be terribly different than they were last semester. So just, take a look at this, and it'll be pretty much the same order, pretty much the same material, maybe a little bit more polished this year. We'll see how it goes. Slack, make sure you get on there. Everybody's pretty much all signed up, but there's a sign up link right there. Just use your St. Martin's email address. Sign up or subscribe to those 2 channels for this class, and then you'll get all of the updates, and you can ask questions on there. Do that a little bit more. I mean, there were some people who did it last semester, but I think more and more is good. The schedule, the first 9 weeks we'll be covering system dynamics material, and so we'll be using from the notes. Notice I put in a new column this term, where there's a notes. My notes, the dynamic systems notes, chapter 5 we start in, we go through chapter 11. And then in the Rowell and Wormley text, we're going to bounce around a little, but go 8, 9, 10, and then go back and do fluid and thermal elements, which is kind of back towards the beginning. And then we'll pick it up at 12 through 15. And then we'll have a midterm exam. So there's only 1 midterm exam in this class instead of 2. So there's going to be 1 over the systems material, and then the final exam. So the final exam is going to be essentially mostly focused on the controls material, the last 7 weeks of the course. So think of this as being a 10-week course on system dynamics, and a 5-week course on controls. And there's going to be like a final for each one. And that's how the midterm and the final exam are laid out. This midterm exam does not happen until after midterm grades are due. So for a while, your only grade's going to be your quiz grade, which doesn't always reflect what happens after the exams. But as long as you're doing them straight up and not using your friends for the quizzes, then usually there is a correlation there. Then we switch gears, and I have the controls notes as well. So dynamic systems notes run out, and then we do controls, which is a separate set of notes, but I'll let you know when we get there. It's going to be a while. And then we switch over to the NEAS textbook. And we do cover a pretty good chunk of NEAS, so it's not like we're not going to cover the NEAS textbook. We're definitely going to be covering the NEAS textbook. I mean, it has 13 chapters. We're going to skip chapters 4 through 5, or 2 through 5, because our system dynamics modeling is pretty much what those chapters 2 through 5 are. So we'll skip that. The assignments are already up there. Starting in the Rowland Wormley chapter 8, we go through and we start to do NEAS problems. Here towards assignment 10, there are 13 assignments. There are only 2 weeks off this week and the week after the midterm exam. There's no homework those 2 weeks. Otherwise, there's homework each week, and there will be a quiz associated with them as well. So remember how this works. There will be a quiz over essentially the homework problems to sort of spot check your homework. Now, you'll log into Moodle, and you'll take your quiz, and yes, there's a bug in Moodle, and it's still there, and I don't know what we're going to do about how to like get everybody in the right section and whatever, but we'll figure that out when we get there. I'm just being a squeaky wheel right now about that and hoping that somebody will fix it eventually. So don't cheat or I will fail you. I have done it, unfortunately. So 25% quizzes. So cheating on them doesn't really make a lot of sense, because if you cheat on them and then you fail the exams, you're still going to fail the class. So midterm is 35, final is 40. Obviously, this class is exam heavy in terms of your grade, and really just down to 2 exams. So I think there are, if there are any outstanding like test anxiety issues that haven't been addressed, I would encourage you to try to get those addressed before we get there, because those grades are going to be very impactful. So there are resources available, and if you need connection to any of them, let me know. But being like present and ready to go on those exams is going to be really important. So I encourage you to really think about like preparing for those exams as we go through the material. I want you guys to be understanding the material as we go. And I think that in some ways the best way to do that is to remember, like, okay, I need to be able to do these things myself from a fresh problem that I can't talk to anybody about in a sort of heat of the moment situation. So starting to prepare yourself for that is good. It's good. Okay. Any questions on this? Did I miss anything? I feel pretty good about it. Okay. All right. Well, I'll see you guys on Wednesday. Don't forget to bring your notes.